Welcome back to the class Computational Neuroscience, Neuronal Dynamics of Cognition. We'll continue our discussion of population activity, and so far we have been restricted to full connectivity. That's not very realistic. In biology, a network is not fully connected. We have seen that there are probabilities of connection, so we have random connectivity. And so the question arises, can we generalize our mean field arguments to the case of random connectivity? So random connectivity comes in two different flavors, and we'll discuss both. The first one is here on the right-hand side. For a given neuron I, in a network of, say, 5,000 neurons, you pick exactly k connections. In this case, for example, k equal 4, this neuron gets exactly 4 inputs. If you now go to a network which is twice as big, and you look again at a neuron I, it will still receive exactly 4 connections. Now the other possibility is that you say have a fixed probability. For example, p equal 0.1, 10% connection probability. Then if I'm in a network of, say, 30 neurons, then this neuron I would receive 3 connections. The same neuron I in a network of 60 neurons would receive 6 connections. So it would receive more inputs. Now for both cases, we'll ask whether we can calculate the mean input to neuron I and whether we can calculate the population activity. So our aim is, as before, to predict the population activity. And what we can use is just the connection probability and the values of the weights. And of course, we'll, as before, use the probabilities of the neurons, and we assume a large population. So n is really large, n goes to infinity, maybe n is 10,000. And here is a simulation of integrating fire neurons. I'll tell you in a minute how this works. And what we observe is that we have this state of asynchronous activity with some mean value A0. This is the value we would like to calculate. And in order to calculate this, we'll see that we will need the typical input into one of the neurons, which we will call I0. And this graph shows that in my network of, say, 5,000 neurons, 2 different neurons have a very similar mean input. Let's try to understand how this happens. In order to explain the formalism, let me make a little detour and introduce the integrating fire neurons to those who are not familiar with these. So I have here a neuron, and I can plot the input current, and the input current would be for each spike that arrives. I have an input current pulse, where one of these spikes, for example this one here, is my spike emitted by neuron K and spike number F. And so this part here, this would be the synaptic current pulse or excitatory postsynaptic current, alpha of t minus TKF. So this is the input current for neuron I. Now I take this input current and put it into a differential equation for the membrane potential. And if I take this total input current, and as before, what matters is the sum, so this is my input current. Now I take this input current, put it into this differential equation for the membrane potential, U, then this will start to increase, and at some point it will hit a threshold, theta. When it hits the threshold, I say, okay, this is the moment when the neuron fires its spikes. And afterwards, we reset, and then we use the remaining current to integrate again up, and maybe we hit the threshold again here, reset, and we integrate again up. So this is an integrate and fire model neuron, and it's driven by spikes that arrive stochastically. They arrive because this neuron is embedded in a network. Now, this neuron is embedded in a network, and I'm interested in the total current that this neuron receives. And here's the current of neuron I. This is one of these traces. It goes up and down like this. And then I can have another neuron K, and it would be the remaining trace. So I'm interested not in the fluctuations, but I'm just interested in the mean current. And this mean current will drive the other neurons, and as a result, they will generate this population activity A of t that we have here. Okay, so let's work on this current expression. What is my current? II is the sum over all neurons J, all spike times Wij alpha of t minus tjf, and that's it. That was the current I had shown before. Now let's do the same trick that we had in a previous section. Let's write this slightly more complicated. We use the delta functions. We write alpha of s, delta of t minus tjf minus s ds, which is the same. And then I have my sum over j, I have my sum over f, and I have my wij. And for wij, let's assume that the weights that are present, so not all the weights are present. Most weights are 0, but there's a probability p that the weight is non-zero. And for those that are non-zero, I'll take a weight w0 divided p times n. So this is just a constant, but I've chosen the constant in a particular form that makes it easy to do the following calculations. Okay, now let's collect terms. I've here my spikes, and this is sum over all neurons, all spikes, and I also have a 1 over p times n. I have n neurons in my network, but the probability that there is a non-zero connection is just p, so that each neuron receives p times n inputs. And it's just over those non-zero weights that I take this sum. Okay? This is limited to the case that wij is non-zero. Now I will argue that this is, as before, w0 times alpha of s population activity of t minus s ds. Now, before we had sum over all spikes of all neurons. Now we have something similar, and let me explain why this is still a population activity. So, these are my n neurons in the population. I have n neurons total, and as before, these neurons emit spikes. Now what this formula here tells me that my neuron I does not get input from the whole population, but this neuron I gets input from a subset of neurons. For example, from this neuron, from this neuron, from that neuron, and from that neuron. So this neuron does not take the whole population activity, but it looks at a subset of neurons. And this is very similar to the discussion we had earlier when I said you can estimate the population activity by not looking at the whole network, but just looking at a test set, a subset of neurons at which you look and over which you average. And that's what this neuron is doing. And how many neurons are in the test set of this neuron, the test set for the population activity? Well, it's just p times n. So this neuron, I, actually sums over all spikes, all neurons, in its test set of size p times n. So this is a sample of the population activity, for neuron I. Now there will be another neuron, K, and this other neuron will also take a subset of inputs. It's an independent subset, it's an independent sample of neurons that will drive this neuron I. And it's also a sample of size n test, p times n, and this is with the same input current drive, just that the activity is estimated from a slightly different subset. Some neurons might be shared, others are different. It's a slightly different subset, but overall, these are subsets that all look at the same global population activity. So in the end, the input drive to neuron J will be very similar to that of neuron I. So in the end, it doesn't matter whether I look at neuron I equal 10 or I equal 25 or neuron number 3021, I will end up with nearly the same input current. So the total input current is I0, and I0 is this expression here. This is the synaptic part, and then I will also have the external part. And from this point on, I can exactly repeat the arguments that we had before. The population activity is equal to the single neuron activity, but for a single neuron I can use the gain function, the Fi curve. The gain function depends on the total input. The total input has two contributions. It's a contribution from the external input and the synaptic drive. And the synaptic drive depends on A0. And now you see that the construction of the mean field argument and the construction that we do graphically for its solution is going to be exactly the same. So yes, we have extended the mean field argument to the case of stochastic connectivity. Now let's look at a couple of simulations with integrated fire neurons. So here it's fixed connection probability of 0.1. I have a network of 5,000 neurons. So typically each neuron receives 500 inputs. You see the input current of two different neurons in the network, and you see the population activity. Now I increase the network size, and when I increase the network size, I pick the non-zero weights with this value, which has changed because now n has increased. So weights have become twice smaller, but since I draw weights with probability p, I have twice as many non-zero weights. And now you see that the typical input is the same. What has changed is just the amount of fluctuations. The typical population activity is the same. What has changed is just the size of the fluctuations in the population activity. So this was the situation for fixed probability. We compared two different network sizes. Now let's do the same for the case of a probabilistic network where each neuron receives exactly 500 inputs, in which case the weights, those weights that are non-zero, all have the same value, W0 divided by K. And now you see again, I have a typical input which is the same for both neurons, and it's the same whether it's a network of 5,000 or 10,000 neurons. Now the size of the fluctuations also stays the same. Why? Because we said that each neuron draws a sample of the population activity, and the sample size is K, and K does not change between the small network and the large network. The population activity fluctuates around a constant value, A0, which we can predict, which is the same on the left-hand side as on the right-hand side. And the fluctuations have decreased a little bit. Why? Because to plot this, I average over 10,000 neurons. So just by this larger sample size in the plot, I've slightly reduced fluctuations. So far, I have focused in the discussions on one single population. Now, neurons come in two principal types. There are excitatory neurons and there are inhibitory neurons. Now, for the excitatory neurons, I already discussed the total input current. as a function of time, if the excitatory spikes arrive here, so I look at one neuron, it gets excitatory input from a subset of the other neurons, and the total input, the total excitatory input will look like this. But this neuron will also get inhibitory inputs from a subset of the inhibitory population of neurons. As a result, there are spikes coming from the other population, from the green population, which also cause some response and which will also add up, and I draw it downward because it's inhibitory. Now, if you adjust the weight parameters for the inhibitory connections and for the excitatory connections appropriately, then you will see that the total input is always very close to zero. It fluctuates around zero. So what drives a neuron, say an integrating fire neuron, towards the threshold is not the mean input, which is very close to zero, but it's the fluctuations of the input. So the mean input is zero, which means it's balanced between excitation and inhibition, but the fluctuations can still drive a neuron across the threshold. So the appropriate scaling for the weights so that the mean is zero and the fluctuations are big enough to drive the neuron towards the threshold is in this form, where it's the square root of the probability of connection times the number of neurons in the network. And this allows to keep the mean input always close to zero. But if you increase the network size, the variance of the input, which means the amount of fluctuations, roughly remains constant. And this is simulation again with integrating fire neurons. On the left-hand side, it's 5,000 neurons. On the right-hand side, it's 10,000 neurons total. Out of the 5,000 neurons, there's 4,000 excitatory and 1,000 inhibitory. And you see that we have a value of the population activity and hardly changes between the left and the right-hand side. And the input here is not really balanced at zero. It's slightly above zero. I have a certain mean. And the size of the fluctuations also roughly remains the same in the big network or in the small network. What changes is that the trajectories become a little bit smoother. So we have these kind of highly volatile trajectories that go up and down are very typical for neurons in vivo that are measured in the live brain. And this is an indication that this balanced regime, where excitation and inhibition roughly cancel each other, might be the regime in which the brain is operating. So what are the next steps? So far, I have focused on a single population. However, this single population is maybe just excitatory neurons in layer 2 of one particular cortical column. This population of neurons will be connected to other populations of neurons and will receive input from other populations of neurons, from other cortical columns in the same cortical area, and even from other areas. The framework that I've discussed this week is general enough to extend to the situation with multiple populations. And we'll use this in the following sessions, for example, for applications in visual processing and applications in decision making. The drive of a single neuron, in this general case, is the activity of the network onto itself, and it's also the activity that it receives from other populations K. And the population N sends its activity to other populations that receive input from this first population. So instead of an interacting network of neurons, we now have an interacting network of neuronal populations. And that's the level at which it is useful to discuss cognitive processing in the brain. So let me summarize. We have gone a long way. We have started off with neuronal populations, population in cortex, for example, a set of neurons, excitatory neurons in one specific layer of a cortical columns. I've argued that these are fairly homogeneous populations. And now for such homogeneous populations, we can write down a mathematical framework that allows us to predict the population activity based on neuronal parameters, based on connectivity parameters. Now, this was just one neuronal population. In the next weeks, we will go on and discuss the interaction between different cortical populations. And that allows us to look at specific perceptual and cognitive phenomena. A lot of people have worked on the theory of population activity, on neuronal populations, on the formalization of the mathematical tools. And please have a look at the references. And as always, there's also the textbook available in its printed form and in its online form. For those who have not been exposed to the Dirac delta function before, they may also want to look at the appropriate chapters in the book or at the videos that are part of the references. I hope you enjoyed it. See you again next week.